Welcome to Freeslate's webinar on the introduction of DOE, design of experiments, and its use with parallel automation. My name is Justin Fisher, and I'm the Senior Product Manager at Freeslate, and I'll be your host for today. Today you will learn about applying DOE principles to help efficiently develop chemical processes with some real-world examples of their use. We're really pleased to have Dr. Paul Murray from Paul Murray Catalysis Consulting joining us today. I want to remind you that we'll conclude today's webinar with a brief question and answer session at the end of the presentation. Before we begin, let me invite you to submit questions using the chat window on the lower left-hand side of your console. Any questions that we do not get to will be answered privately on a follow-up email, so please feel free to submit questions throughout the presentation. Our speaker today is Dr. Paul Murray. Dr. Paul Murray is a consultant providing expertise and training in the fields of catalysis, design of experiments, principal component analysis, and process development. Paul is an experienced scientist with additional expertise in automation, multivariate data analysis, process development, and problem solving. Paul worked as a process development chemist at AstraZeneca and collaborated with academics at the University of Bristol to develop ligand property maps to enable the use of DOE for the efficient, rational development of catalytic reactions. Paul has been applying DOE in a wide range of chemistries for more than 15 years. To date, Paul has 16 publications and 9 patents. The title of Dr. Murray's presentation today is Introduction to Design of Experiments, DOE, and Parallel Automation.
Thank you, Justin, for the introduction, and thank you, everybody, for coming. So experimental design is a different technique and is different to how people are traditionally trained. When you study chemistry, you learn to change things one variable at a time. So what does this mean? So what we have here is a reaction space, and we have 2 parameters of concentration and temperature, both of which, if we change them, we expect to have an outcome on the reaction. We have no information about this reaction, but we want to try and get this reaction to work, and it is possible to do this. When we come to this reaction, we carry out an experiment, and from that experiment, we get a result. And the result for this reaction is very low. So we have 10% conversion or less in this reaction. We still have starting materials. So logically, people as a chemist would move and increase the temperature. And so we run another experiment at a higher temperature. And so we get another result and we see an increase in yield. And we continue to run experiments at progressively higher temperatures until the reaction starts to fall off. So we've changed one variable one step at a time. On the basis of this, we find the best reaction that we have from changing temperature, and we change another parameter. In this case, we would change concentration. So when we start changing concentration, we start to find that the reaction yield our conversion is going up, we're getting more product. But we hit a maximum of somewhere in the high 30%. So this is looking like the maximum for our reaction. So what do we do now? We have a reaction which is not good enough, and we don't know how to move forward. If we look at it from a development from a chemistry point of view, you have an idea of what you want to do. You have chemistry you want to do. You start with an experiment. We carry out large numbers of experiments, moving in different directions, changing one factor at a time, trying to get the reaction to work more effectively. So we follow a long route, changing many things to try and get something that works. We find something that works, and then we try to understand it. And this is how people are traditionally trained, changing one parameter at a time. By changing a single parameter at a time, you will usually miss the true optimum for the reaction, so you won't find the best that it can do. It is a very inefficient use of resources. We will have carried out, in the example I just showed, more than 11 experiments, and we're hitting a maximum of close to 40%. If that is all that is possible from that reaction, then that's great. But we know actually that there are better available from this. We have very limited coverage of the chemical space, the design space. We have carried out changes in 2 directions, and we have no other information about this. We have no information about how one parameter affects another and whether they interact to have a larger effect. And we also do not know if there is any experimental error in here. So we don't know the significance of the results. There is another way forward. We can use design of experiment. What is design of experiment? It's also known as statistical experimental design, factorial experimental design. And it is an efficient and structured way to investigate potential factors and their cause and effect relationship on an experimental outcome. So what do I mean by that? We have something that we think is important, like temperature or concentration or the amount of base or the type of base, and we change those. We change those for a reason, and that is because we believe they will affect the outcome of the experiment. And by studying it with the experimental design, we can understand what that effect is on the outcome of the reaction, be that yield, be that selectivity, or some other factor. If you choose the correct factors, then you will get a lot of information, a lot of useful information from that reaction. The key to success in experimental design is choosing the correct factors and investigating them over the correct range. In my experience, when people come to experimental design and say it doesn't work, it is because they either have chosen the incorrect factors or they have looked at those factors in the wrong ranges. And those are the keys to getting successful experimental design. When you do DOE properly, you find information out about how the whole system works. And the bit for many chemists that frightens them from this is it involves statistical methods to extract and interpret the relationships. So you need to understand the statistics in the background, but you don't have to be an expert in statistics to use this technique. If you carry out an experimental design properly, it will tell you a lot of useful information. It will help you to understand what factors or variables are important in your process. So is that what temperature, what solvent to run, what concentration, how much base, how long the reaction will take. It will also help you to work out at what settings for those key factors you will get the best performance for your process. It will help you to understand which factors are most important and if there are any interactions between those factors. And at what settings you will have the least variation in the output of your reaction. I have also used this to be able to compare the qualities of material from different suppliers to make sure it doesn't affect your process. So how does DOE work? At the simplest level, you take the factors you're interested in this case, 2 factors, and we investigate each factor at a high and low level. So with 2 factors at a high and low level, we carry out 4 experiments. Based on those 4 experiments, we have a direction of travel. So you can clearly see that for 3 of these experiments, we're getting somewhere around 20% conversion. But for one of these, we're starting to get 50%. So based on this, we have a clear direction of travel towards the best point. So based on those results, you would start to investigate up in this region here. So as we carry out the follow-up experiments, we base the new design on the maximum point that we have achieved so far. And from this, we gain more information. It is important to know that even though the point here for the experiment, this point here, is not the maximum that we've had for the reaction, the experimental design will actually predict results around this. And so we will get this as a prediction from the experimental design. And from that prediction, then, we will have a reaction that works much better, and we will have the maximum for that true reaction. So at this point, you can lie back, put your feet up, and predict hundreds of results from many, many experiments. So if you look at this through trying to understand the process, you still start at the same point. We still have to have an experimental a point to start from. But instead of changing one factor and then another factor and then another factor, we start with the experimental design and we change multiple factors simultaneously, and we look at high and low levels for those. We very quickly rule out the factors that are unimportant and understand which ones are important and in what range. And from this, from the first experiment that we thought of, we're starting to get some conditions which are going to give us much improved reaction. And based on that, we carry out subsequent experiments. And those subsequent experiments bring us to where this reaction works very well. And we are gaining more understanding around the process. And from that, we can actually choose where you want to carry out the experiment. And from a process development point of view, you understand exactly where to carry out that experiment and over what ranges will give you a robust process. Experimental design is a very powerful tool in helping you to gather the maximum information from the minimum experiment. From my experience, it is extremely important to try and generate reaction profiles from each experiment that you carry out. And this is where automation can be a significant aid to carrying out experimental design. So why should we generate reaction profiles? So here we have the results of 4 reactions. These are catalytic reactions where we have changed the catalyst or ligands. We have carried out 4 reactions. We have left the reaction to run for 24 hours. And what you see is that 2 reactions give us 100% conversion at 24 hours. 1 reaction gives us 80% conversion, and 1 reaction gives us 60%. So based on that one experiment, you could pick either Catalyst 3 or Catalyst 4 and run your process with those. But we don't know whether Catalyst 3 or Catalyst 4 are better or if there is any difference between those 2 catalysts. If instead we took a sample at 1 hour and another sample at 24 hours, you see a very different picture. Surprisingly, Catalyst 2, which finishes at 80%, starts at 20%. And also surprisingly, this green catalyst, Catalyst 1, gives almost 50% of the first sample, but then stalls at that point. If you had only taken the reaction samples at the beginning, you probably would have chosen this catalyst. This catalyst is very effective, but it is very expensive. If having run the same reactions, but we take some more samples, we actually get a true profile for these reactions. And the difference from a point of view of taking this chemistry forward is that Catalyst 4 has a cost of about $10,000 a kilo. Catalyst 3 has a cost of $5,000 a kilo. And Catalyst 2 has a cost of $1,000 a kilo. So by taking more samples, we generate much more information and we can understand how this process is working. We also understand that this catalyst here has had something that poisoned it or has stalled for some other reason. So with experimental design, we use a lot of different terminology, and I just want to make sure that I explain those as I go along. So we take an example of a traditional chemical reaction, so an SN2 reaction where we have an alcohol displacing a leaving group to form a new ether product. We have options on what the leaving group can be, so it could be diazo, triflate, mesylate, iodides, or another halide. We have choices of different bases. We have choices of different solvents, what the concentration, mixing, heating could be. So for a chemical reaction, we have a number of factors. So those are the substrates, the nucleophiles, the leaving groups, the bases, the solvents. The equipment that we add, that we carry out the experiment in, whether it's done in batch or flow, and the order of addition of materials together. These factors are discrete, and these factors are more difficult to control and to understand in experimental design. There are other factors like the ratio of the substrate, so how much alcohol you use relative to the other substrate, how much base you have. So the amount of the alcohol, the amount of base, so quantity of reagents, the concentration, reaction temperature, and addition rate. So those are continuous factors or continuous variables. We have levels for those, so we have a low level and a high level. And we have responses. So our responses can be whatever you need them to be. It can be conversion or selectivity, REE. It can be cost. It can be purity. You can also look at this at the environmental impact or sustainability of a process as a response. There are two key factors. There's a key factor here which you will see that is missing, which is time. In my experience, it is better for you to generate reaction profiles and take multiple samples from each reaction. And therefore, I would always recommend that you do not run reactions and vary the time, but that you run the reactions and take samples at multiple times. I also recommend that you do not use yield as a response. If you carry out two experiments under very different conditions, the workup required to get the maximum yield from those may well be different. An example being if you run a reaction in hexane and DMSO, the isolation procedure required will be very different. And you're going to likely add experimental error to your results based on having to do slightly different workups for both of these reactions. So therefore, it is better that you measure your responses much closer to the actual reaction changes that you carried out. And therefore, I would recommend that you use conversion as a response rather than isolated yield. So why should we use automation to carry out experimental design? If we look at the factors that may be important for the SNAR reaction, which I showed a moment ago, we would have the stoichiometry of the two reagents, the equivalence of base, the concentration, and the temperature. So those are the factors that are important. But the base and solvent may also be important. If we look at the continuous factors, the stoichiometry, base equivalence, concentration, and temperature at two levels, and if we look at 4 bases and 100 solvents, that works out as 8,000 experiments. That is not achievable for someone to carry out that many experiments. We can use a technique called principal component analysis, and that's not something I'm going to go into in any more detail today other than to mention it, but I will follow up in a subsequent webinar. You can reduce the 100 solvents to a subset of 9. And from that, you reduce the number of experiments to 720. If we take any of these factors through, still 720 experiments is too many to carry out. If we apply DOE, we can do this in 19 experiments. So 16 experiments plus 3 repeats. But based on these, we can study this in 19 experiments, and we would take 4 to 5 samples from each one of those reactions. And automation will simplify that considerably for you. If we look at a more challenging reaction, such as a catalytic reaction, we add a catalyst. So we have how much catalyst, the amount of catalyst and ligand, what the ligand is, and what the catalyst is. We then start from 51 million experiments. Using principal component analysis, we can reduce that to 41,000 experiments. But that is still too many to run. Even with automation, I don't think many people would start by running that many experiments. Applying DOE, we're talking about running 32 experiments plus 3 repeats. And the 3 repeats will give us the reproducibility and experimental error for our process. And I'll deal with that more in a moment. The design of experiments will help us to improve the answers from our process, or from our chemistry. When you decide to go into experimental design, you have to be much more careful than when you carry out experiments one variable at a time. If you choose to spend a day in the lab and carry out an experiment, and you miss an important factor, and the result of that experiment is that you have no improvement over where you were the day before, you've lost one day. If you carry out an experiment and you carry out 20 experiments over the course of a week, and you use up all of your starting material, and you're no further forward, then you have wasted a lot more. It's a lot harder to recover from that position, and it can be very expensive and a significant waste of time. To use experimental design properly and effectively, you need to carry this out in a very fixed process. The outcome of the design is directly related to the thought that you put in at the beginning. So you have to construct the design and carry out in the right way. So it's very important that you think about your chemistry very carefully and follow the following steps. The first thing is, why are you carrying out the experimental design? So you need to define what the problem is. And often when you start with a process or start with a chemical reaction, you want to improve it. The objective may be to get 100% yield, but you need to break this down into maybe smaller objectives or smaller sets of problems to try and solve. So for instance, you may look to get the highest conversion that you can, and then look at the workup separately. So when you've decided what the problem and objective of the piece of work is, you then need to think very carefully about what factors you're going to investigate. And this is extremely important. And once you've chosen what factors you're going to investigate, you need to think about the ranges for those factors. You then need to think about the response that you're going to measure. If you carry out an experiment and you analyze it for conversion, but you've not analyzed it for impurities that are present in that reaction, you may not be able to go back and get measures of those impurities at a later date if you've not retained the samples or collected the right information. So you may not have selectivity or information about impurities that later prove to be important. So it's important that you think very carefully of the responses you're going to use. Having chosen the factors and the ranges and the responses, you can then create an experimental design to investigate those factors and those ranges. And that will investigate the reaction space in a much more detailed way. Having thought carefully about it and created the design, you carry out your experiments and collect all the data that you need for that. Having collected the data, you need to check that the results are as you would expect and analyze the data. From the analysis, you need to apply your chemical knowledge to interpret the results and make sure that what the design is telling you actually makes chemical sense, and also that they're meeting the objectives that you set out at step 1 and 2. Do they solve the problem? The experimental design will make a prediction about where this process or what setting for these factors will give you the best result. So you carry out that predicted result, that predicted experiment. If the result is as predicted, you've just validated the model and shown that the model is actually explaining the chemistry effectively. If the result is not validated, then it tells you that there's something that you're missing in your analysis. If having gone through this step, you have a process that is good enough or your reaction works well enough, at that point, you're finished. If the reaction is not quite good enough, you can go back and start through this process again, but you're moving on based on the knowledge you've gained from the first set of experiments. So another way to view this is this DOE process wheel. So looking at the aims and objectives, your factors and ranges, the responses, selecting the design, carrying out and analyzing the data, checking the results, modeling the data, and validating the prediction. But from my experience, the reason that most people fail with experimental design is that they don't identify the correct factors. When you look at a reaction, you need to consider all the steps in the process. So it's not just which nucleophile do I use or which base do I use. What's my order of addition? What equipment? Is it batch or flow? What reagents I'm going to have? What additives? What my rates of heating, cooling, mixing are going to be? What grades of material? It may make a difference whether you use an anhydrous solvent or whether you use a base that has added water present. How do I select my factors? You select the potential factors by considering the reaction and the workup separately. You think of the factors, you think of all of the factors having identified them, you either control or vary them. You should investigate or control all factors which are likely to or are possibly likely to cause variability in the experiment. You can choose to fix something at a set point. You don't have to investigate it if you don't wish to. But if you don't control or investigate the factors, you will have poor reproducibility. If you carry out an experiment today and you get 95% conversion and get a good yield from that process, you have very little information other than that experiment worked. If you carry out the same experiment tomorrow and you get 50%, then there is a problem, and you didn't know the significance of the result in the first place. If you've carried out the same experiment multiple times and you get the same result or very similar result, then you have much greater confidence in the result for that. And DOE does replication to help you to understand the significance of the results and give you confidence that you've investigated or controlled the right factors. You should investigate all the factors that can influence the kinetics of your process. The approach that I use when I look at selecting factors is start by using prior knowledge. You need to be careful in applying this. The method I recommend you to use is start with any previous observations you or colleagues have had with that exact chemistry. If you have information about the exact chemistry, apply that. If not, you can look at literature or from other colleagues for closely related for the exact chemistry. If you have no information on the exact chemistry, you can then move back to related chemistry. But be careful in how closely related that chemistry is, because in some chemistry, simply changing an electron donating or electron withdrawing group can completely change the outcome of the chemistry. So as much knowledge as you can apply directly from something that is exact substrate is much more trustworthy than chemistry that you will get elsewhere. It's important that you choose factors that are likely to answer your experimental objectives. If you're trying to get a more sustainable process, then you don't want to use damaging reagents or very toxic solvents. If you're trying to get a cost-effective process, you can use catalytic processes, but the catalysts have to be at extremely low levels or be recycled efficiently. So there is no point in looking at a process which is stoichiometric quantities of a very expensive reagent if your cost is a significant portion or a significant factor or response you're going to have. We will see shortly that it is far more economical to look at many factors using screening design. If you skip a factor, if you fix a factor and later find that it is important, you may have to go back and start from the beginning because you don't know how that factor may interact with other factors. So when you go to factor identification, I recommend you use a fishbone diagram or something along these lines. And here we have the reagent. So here I have reagent A, so that will be my electrophile. Reagent B is my nucleophile, my base, temperature, the heating rate, the cooling rate, what solvent I'm going to use, how much solvent I'm going to use, the order of addition, the rate of addition, the mixing, the type of equipment. These are all potential factors. From my experience, if you cannot identify at least 12, but preferably 15 to 20 factors, then you have not thought about your process sufficiently. This is not saying that you will investigate 15 to 20 factors, but you should try and identify all the factors that could be important. So just going back, we have factors which are continuous, like temperature and stoichiometry. They are called continuous because you can choose any level for those. So for example, from temperature, you can be at 0 degrees or 100 degrees. The only limitation with this is your equipment and ability to achieve those settings. Excuse me. We then have discrete factors, and that's reagents, solvents, types of equipment. They're discrete because they're constrained by the availability or existence of that material. So you can have different types of equipment, you can have different solvents, you can have different bases. But how does one relate to another, and how do you choose another one? That is much more difficult to do. And an example of discrete factors in solvent is what's the difference between hexane and DMSO? And if you had to run a reaction, which solvent would you choose? Well, this can be very tricky if I tell you from my experience a reaction such as a Heck reaction can be significantly affected by the solvent. And for an electron-rich Heck reactions normally work better in polar aprotic solvents. From my experience, I have seen that the selectivity of an electron-rich alkene in a Heck reaction can be completely changed by using a solvent such as hexane instead of DMSO. And therefore you can select between alpha and beta addition to the alkene. So solvents can play a big role. So having selected factors, you then need to select the levels for those factors. You want to choose ranges that are meaningful. So if you're going to look at the amount of reagent that you add, having starting from twice as much reagents as you need is not going to help you to understand how significant that factor is going to be over that range. So looking at 2 equivalents and 5 equivalents of a material in excess is not really that meaningful. But if you need 1 equivalent, there is no point in looking at it from a half equivalent to 1.5 equivalent. So choose a range that will be meaningful. It needs to be possible. So there's no point in choosing a range of a temperature range where you're not going to be able to achieve the temperature that you're looking for, or that your reagents will boil off and you will get a different result. So they want to be meaningful, they want to be possible, but you want them to be relatively wide. Because if your range is too small, so if you, for instance, look at temperature at 30 and 40 degrees, but you need a higher temperature, you may have to do lots of sequences of increase in temperature to achieve that. So I would look at a wider range for temperature. So it's a case of choosing things that are meaningful but as wide as practical. When you carry out experimental design and we've chosen our factors, we've chosen our ranges, there is a neat trick that you can carry out. And this is where you pick 3 of the initial set of experiments you carry out. So you carry out the experiment where all or most of the factors are at the lowest setting, and you carry out the other experiment where all or most of the factors at their highest setting, and you carry out one of your 3 midpoints as your first 3 experiments. So if all the factors at the lowest setting or the highest setting give you an outcome that the reaction has not worked, then you know that there is a problem, that you either have too low a setting or too high a setting. So at high setting, maybe you have decomposition and impurities. At a low setting, maybe you not have things hot enough for the reaction to progress. So if you have those, you can change the set point for the rest of the design. If the lowest and highest settings give you the same results, then that tells you that the settings are not different enough from each other to achieve the result that you want. And the midpoint gives you some indication of the direction of travel. So it is good practice or useful for you, particularly if you're not using automation, that you carry out the factors in this way. And that means that you can get some information and be sure that you've chosen the right ranges for your factors before you carry out the rest of the design. So you've only carried out 3 experiments rather than 11, 19, or 35. When we're selecting responses, we need to make sure that we collect enough of the right type of data. And you want to maximize the information from each experiment. The responses need to give you accurate and consistent results. If you cannot get accurate and consistent results, then you're going to have more experimental error. And the error will be added from the analytical side rather than something that's an indication of changes within the chemistry. It's important these responses closely replicate the actual experimental outcome. And you want to be able to get the minimum variability between repeats. So the change that you're measuring with your response needs to be as close to the event as possible with the minimal workup so that you add the minimal error to your results. The most important part is that the variation between good and bad results must be much larger than the noise that you have in the analytical measure that you're using for this. So experimental design will tell us what factors are important and what the ranges are important. The other thing that experimental design will tell you about is interactions. So interactions are very simple, where you have two things, you change them together, and you get more of an effect than you do by changing either. So if we consider wind and temperature, you can have a temperature outside, and depending on the wind and the direction, you will have what it feels like. So the actual temperature that it feels rather than the temperature it is, or potentially the wind chill factor. If you consider time and temperature for food, you can get can affect the storage life for food. The simplest thing with interaction, there are two types of interaction. You can have interactions which work together to give a positive effect, so they can be synergistic, so you get an improvement in your product or yield. Interactions can also be antagonistic, so it combines together, they give a bad outcome. A particular example of that is drug combinations. The simplest thing with interactions is if you have an interaction, 2 and 2 will not give you 4. 2 and 2 could give you minus, or could give you 100. Now, DOE involves the use of statistics. But please don't let this put you off. Just try and explain very quickly a little bit more about DOE. So we have a set of experiments. We have two factors in temperature and time, and we have a response. Now, at these, we have temperature which is low. So each factor has a low setting and a high setting, and we have a response. So with experimental design, we will convert the low values to -1 and the high values to +1, and we have our responses. We have chosen these factors because we believe they will have an effect on the outcome of the reaction, and we've chosen this response to measure that effect. We also have a potential interaction here. So our response Y, we have our factors X, so temperature and time, and these factors are chosen because we believe they will affect the response Y. And we have some measure of experimental error. So we use a Taylor expansion. So we have something for the center point. We have something for x1 being temperature, something for x2 being time. We have something for the interactions, and we have something for the squared terms and the errors. So this factor this is taken forwards, and this can be solved. So the Taylor expansion is what is used to try and work out the relationship between the factors we've investigated and the responses. Or there is many different versions of software available, and all of those softwares will work out and analyze and interpret those for you, so you don't have to worry about doing the statistics yourself. How do we choose the right design type? So if we look at factors, if we have 2 factors, we would need to look at that in 4 experiments plus 3 repeats, so 7. That's an easy number to achieve. If we have 6 factors and we were going to look at all the factors at high and low levels, that will be 64 experiments plus 3. If we have 12 factors, then that's 2 to the 12. That's 4,096 experiments, and that is something that is just not going to be achievable for someone to take forward. So the number of experiments grows exponentially as you identify additional factors to investigate, but don't worry about that. We can use fractional experimental design to provide most of the information with many less experiments. There are many different types of designs that we can use, and each of these designs have been developed for specific reasons. So we have screening designs, which Fractional factorial designs are one type of that, and they allow us to investigate many factors or potential factors over different ranges to identify where the reaction is going to work. We have optimization designs, which can be used to further improve a reaction when you've identified which factors are important and really to optimize the process. We have response surface designs, which are quadratic designs, to give detailed knowledge about a process. Response surface designs are something which, in my experience, only get used in a process where you're looking to make a commercial process and right when everything else is fixed. And I would do probably 90% of my work in screening and optimization. 7 or 8% of the work in response surface, and a little bit in robustness design. And the robustness design is designed to look at when you've identified which factors and which ranges, and you're planning to run something on a large scale, and you want to be really sure that all of the ranges that you're going to set, the variation you allow in the process will give you the desired outcome. So I already said that for 12 factors, you would be running over 4,000 experiments if you were to run each factor at a high and low level. Using fractional factorial designs, we can greatly reduce these numbers. So this table will show you some information about how the number of factors relate to the experimental design. So if you have 2 factors and you look at each factor at both levels, then that's 4 experiments. What we have here then are some designs which are measured in with red, yellow, and green. Ideally, you would choose to run a design in the green box. So for instance, if we look at 6 factors, we can investigate 6 factors in 32 experiments, and that's a half factorial. So we're running half of the experiments because we would have been running 64 experiments if we looked at all of the experiments. In a half factorial, this is a resolution 5 design, and a resolution 5 design enables us to look at all of the factors and the interactions and understand them. If we chose to run 6 factors in 8 experiments, we would be running a resolution 3 design. In a resolution 3 design, we can rule out some factors, but we'll have no information about the interaction. And when we see a factor as being important, that factor may be confounded or confused by having some interactions hidden behind the data. It is possible to use a quarter factorial, so 16 experiments. And we can run that 16 experiments and we will get most of the data. That is a resolution 4 design. And so we have a choice of different types of designs and different numbers of experiments that we can carry out. In my experience, I regularly use resolution 4 design. I can understand clearly which factors are important, but I also know if the interactions are important. The problem with the resolution 4 design is that you may have 2 or more interactions which are confused. So you've not carried out enough experiments to be able to pull apart all of those interactions, but the software will tell you which interactions it could be. So if we just look at some design types, so a Pluckett-Burnham is a screening design or a resolution 3 design. 4 factors would require 8 experiments. 6 factors would also require 8 experiments. For a fraction factorial design, 6 factors would also be 8 experiments, but 12 factors would be 16. So resolution 3 design is many less experiments, but you lose a lot of information. The resolution 5 design will provide the maximum information that you're likely to want, so it'll explain clearly which factors are important and their interaction. But if you have 12 factors, that requires 256 experiments. And that is too many experiments to be able to interpret, or to be able to carry out. And so a resolution 5 design will allow you to get the maximum data from this. If you look at a de-onion design, the optimal design, these are mathematical designs that are designed to try and explain some more information. I won't go into those further today, but we have a response surface design. 4 factors for response surface design. Each factor will be looked at least 3 levels. So we have 24 experiments. So we have to run many more experiments for 4 factors. But if you've got 6 factors, then you're running a much larger number of experiments. Response surface design should only be considered right at the end when you really understand which factors are important. So I'm now going to demonstrate how DOE can provide you maximum information from a specific example. The example I'm going to show you is a dehydration. It's an acid-catalyzed process, and 3 factors were identified as possibly being important for this. So the temperatures that were investigated was temperature at 120 and 160 degrees, the concentration from 1.5 to 2.5 molar, and the different acid catalysts that we were going to use, whether it was phosphoric acid or sulfuric acid. In this case, a resolution 5 design was carried out in 11 experiments. Because we only had 3 factors, we were able to do this in a that you look through the DOE process. We want to optimize this reaction and maximize the yield. We have identified some factors. But what factors have we missed? Well, we could have looked at solvent effects on this reaction, but we're using aqueous acid, so this was decided to run under aqueous conditions and not to add an organic solvent. But if you looked at different acids, then it could have been beneficial to look at different solvent. You could also look at this with different equipment, whether you run it in batch or flow. So we've identified some factors. We have ranges for those. We create a design. Experimental design looks like this. We have an experiment order. And we have a run order. It is important that you run the experiments in a run order, which is different from the experiment order. The reason for that is that the 3 experiments here at the end are a repeat. And those 3 repeats should be run at different times so that we get a true measure of the experimental error, especially if it's possible that we would have a change over time. So we create a design, we carry out the experiments, and we get the response. So we have our response for yield. If we look at the results, we can plot this to see the results, and what we see is, so the green dots are the results for each of these experiments, and the number on each one of these dots is the experiment number. In blue are the 3 repeats. So what we see here is we have excellent replication, so the 3 experiments are giving very close results, and we have a spread in results. So we have some reactions that didn't perform very well, and we have some pretty good reactions. So based on this, we take it forward, and we can work out which factors are important. So we have temperature is hugely significant in this reaction. So this green bar, so temperature here, this is showing the coefficient. The size of this green bar is telling us how significant it is. We have an error bar on this because we've carried out a replication. In this case, we have the concentration. The concentration has a negative effect. So what that's saying is temperature has a very positive effect on the yield or conversion, whereas concentration has a negative effect. So at higher concentration, we get lower yield. We have 2 acids here. So we have the 2 acids, one's having a negative and the other's having a positive effect. But the error bar goes through the origin. So what this is saying is that the acid on its own is not significant. So why is it still in there? We'll see in a moment. So we have a potential interaction between temperature and concentration, temperature and the catalyst. So this is temperature in one catalyst, temperature in the other catalyst, and a potential interaction between concentration and the acid. We take this forward. This creates a model which explains all of the data. So we explain 99% of the results and is very predictive. We have no experiments which are outliers, so we have a normal probability plot that shows us our data. You'll have hopefully remember from the previous coefficients plot that we had interactions here which were very small and the error bars went through the origin. So those have been removed. We've refined the model to simplify it. But we have an interaction here between temperature and acid. So in this case, this one we have temperature and phosphoric acid, and in this case, temperature and sulfuric acid. So what we see here is temperature, and an interaction between temperature and sulfuric acid has a positive effect. And here, concentration and as well as temperature with an interaction with phosphoric acid has a negative effect on the outcome. So the model will be slightly improved and simplified. We look at this to see how well this would predict our results, and you can see very, very well that all of the results are sitting on this line of the plot of observed versus predicted results. What this tells us is the model predicts very accurately the results that we see. We do have an interaction between temperature and catalyst, and this is an interaction plot. So what we see here is the temperature along the bottom. So we have low temperature and high temperature, and we have the effect of that temperature on the different acids. So low temperature with sulfuric acid is giving us a result of about 48%, whereas high temperature with sulfuric acid is giving us a result of over 80%. If you had carried out and investigated both of these acids at 120 degrees, you would have chosen phosphoric acid. Having chosen phosphoric acid, you may have looked to increase the temperature, and you would have found a result of 70%, but you would have excluded sulfuric acid. If you had not carried out an experimental design, you would have missed that sulfuric acid at higher temperature can give you a much higher yield. So if we move forward from this, we can get a contour plot, and the contour plot is basically just showing you the effects of temperature and concentration against the response yield. Contour plot is set to look at blue being low to red being high. So what you see is that the maximum yield that you could get, or conversion you'll get with phosphoric acid, is about 70%, where you have low concentration and high temperature. But if you look at sulfuric acid, you can get a much higher result. The advantage of having carried out experimental design is that this can now go and predict where you should actually operate this process. So the predictions that are made based on the design that we have carried out is that if you reduce the concentration further and you increase the temperature, you can actually get 100% conversion. So having carried out the design, having understood which factors are important and not important, we have now created a prediction. We carry out that prediction, and that validates the result. If the predicted experiment gives you the result that you wanted, then you know that the reaction, that the model is accurate and is predictive outside the region we've investigated. At that point, you know how significant your results are. Okay, so that's experimental design, and that's how it works. So thank you very much. If you have any questions, I'd happily try to answer.
Okay. Well, thank you very much, Dr. Murray. We'll now have a question and answer session. We've got about 10 minutes available for us. Please continue to submit your questions that you may have been incubating throughout that great presentation, the chat window on the bottom left, and we will try to get through as many as we can. So I will, just a quick reminder that once a recording of this webinar will be hosted on Freeslate's website and will be made available to you guys. So let's have a look. What have we got? First question here, Dr. Murray. Can you just cover again, what does resolution mean in factorial designs?
Okay, that's a great question. So if we remember at the beginning, when we talk about the experiments, we look at the number of factors that we think are important, and we think of the ranges of those factors. And based on that, it would suggest a large number of experiments that you have to carry out. So the resolution is something that comes in when we run a fractional factorial design. And really the resolution is telling us how much information we're going to get out of that design. and it allows us to make a decision about how many experiments we're going to run versus the number of factors that we're investigating. So a low resolution design, like a resolution 3 design, will allow us to rule out factors that are not important, but will lose information on the interaction. Whereas a high resolution design, like a resolution 5 design, will provide all of the information about the number of factors, about each of the factors, but also all of their interactions. So the resolution is telling us the amount of information that we can get, and the higher number of 5 is much better than the lower number of 3. Sometimes we can't carry out all of those experiments, and therefore we have to choose or compromise as the number of experiments and the resolution of the design we're going to run.
Interesting. And so a follow-on question has just come in. So how many experiments should I run?
That depends on your chemistry, on the complexity of the chemistry, your ability to run those experiments, and how long it takes to carry out those experiments. Typically, I would run in the region of 19 experiments, so 16 experiments plus 3. But for more complicated chemistry, and if automation is available, then I would look at up to 35 experiments, or 32 plus 3. With 32 experiments, you can look at 12 or more potential factors in a single experimental design.
Okay, interesting. So another question that came in, how many factors are likely to be important?
Again, this depends on the complexity of the chemistry. Sometimes you'll be lucky and 2 or 3 will be important. If you're very unfortunate, you might have more than 6 factors to be important, but I would typically expect between 2 and 6 factors to be significant, but that's having started from 12 to 18 potentially significant factors.
I see. And why not just use high throughput experiments? Why not just brute force it?
Yep. Okay, so if we go back and look at the numbers of experiments that I showed in the 2 tables, where we have 6 factors for something like an SNAR reaction, so stoichiometry, temperature, concentration, the amount of base, and solvent and base as factors, that's 8,000 possible experiments. So without some sort of rational approach, 8,000 experiments is difficult to do even with high throughput screening. As we move to something more complicated like a catalytic process, then that's 52 million, and I don't think anyone would try to run that.
I see. So the advantage is very clear as you apply the methodology.
Very, very clear.
Okay. So I think that is all the questions we've had so far. So what I'm going to go and do is wrap up the call at this point. So before we go, I'd just like to remind you that you can visit our website to see previously recorded webinars on a range of topics that are associated with the application of high throughput research solutions, including from Freeslate. They're located in the Technical Resources section of the upper navigation menu and can be found under Learning Center. A recording of this webinar will be posted there, so you can go ahead and watch and fast forward and rewind and digest the topics at your leisure. So that concludes today's webinar. On behalf of myself, I'd like to, and Freeslate, I'd really like to thank Dr. Murray for taking the time to give this presentation today. I'd like to thank you all for attending, and we look forward to seeing you at future events. So everybody go ahead and have a great day.